Okay. Thank you very much, and thanks organizers for inviting me. It's always great to be back in California, where I did my postdoc like ages ago. So as Marty already kindly mentioned this morning, I'm at the peak of my jet lag right now. I probably should be talking about deep sleeping instead of deep learning. Anyway, so if I sound a bit incoherent, please forgive me, and please don't ask any difficult questions. Yeah? Okay, so deep learning of dynamical systems. I want to start with a brief primer on dynamical system theory. I would assume that many of you are amply familiar with dynamical system theory, but for those of you who are not, maybe it's good to have at least some introductory slides. And for those of you who are, please forgive me that these slides are quite superficial, but I will make some connections to neuroscience and psychiatry. Then the main part of my talk will be about our methodologies, and I will spend actually quite some time on algorithmic and some mathematical details because they are important for explaining where the power of these systems in this context comes from, and also because that's basically the main work we are doing these days. And then I want to round up with illustrating how you might use that in psychiatry. Okay, so what are dynamical systems? So as I said, most of you are probably familiar with that. Nevertheless, let me briefly say it's basically systems that we describe that evolve in time and maybe along other dimensions like space, and which we describe by systems of ordinary or partial differential equations in continuous time or in discrete time by recursive relations. And usually, most people, at least in experimental domains, look at variables in terms of time graphs, how they evolve in time, and we might want to give them here some psychological meaning. So one important tool or representation in dynamical system theory is that of a state space. State space is basically the space spanned by all the dynamical variables of our system, and it shows the temporal evolution of our variables as a trajectory in this space. So each time slice here would be a point in the state space, and if our system is deterministic, then knowledge about the point in the space would completely allow us to predict the future fate of the system. Okay, so these state spaces or phase spaces are filled with a lot of geometrical objects, like for instance attractor states, and this is my favorite toy examples to illustrate that or introduce that. So assume you have a population of excitatory neurons or pyramidal cells which have a positive feedback loop going on here, and you have a bunch of inhibitory interneurons which give rise to a negative feedback loop. You just describe the system by two differential equations, find rates of the excitatory and inhibitory neurons. Then you have a two-dimensional state space, and if you plot the derivatives anywhere in this space, you get these flow fields which basically tell you how the system evolves in time. What you can see here is that there are 2 points towards which activity seems to converge, and these are indeed attractor states, so-called fixed point attractors. Formally, they are given by the condition that both these derivatives go away, so each of these lines with one of these derivatives vanishing is one of these null clans. And you see that this whole space is sort of separated into basins of attraction. Now, if you, for instance, apply a stimulus to the system and you have this sort of system which can be bistable or multistable, so which expresses many of these different attractor states, then you can basically, it will keep a sort of a memory of the stimulus, and you can switch it forward and backward between these these different attractor states by stimulation. So generally, attractors are geometric objects in these state spaces at which activity stays bounded, to which activity will return after perturbations, and to which activity converges from some neighborhood which we call the basin of attraction. So there is plenty of evidence for multi-stability and different attractor states in the nervous system. So this is probably one of the oldest ideas that go back to work by Joachim Fussbar and Pat Gottmeier-Keech, starting in the 70s already, where they found these sort of memory cells which switch into a high activity states during delayed periods of short-term memory tasks, and that is, for instance, one of these findings that might be explained by multi-stability. In fact, that's a quite long-standing idea in computational neuroscience. So I guess many of you might be very familiar with that, yeah, but I wasn't quite sure, what type of kind of crowds I would meet here, and how many of you are from pure mathematics and might not be so familiar with ideas in computational neuroscience. So I thought I'd introduce that. They go back at least to work of John Hopfield, these attractor memory networks, where the idea is memories are stored by fixed-point attractors, and this process of memory retrieval is basically a convergence to one of these attractor states in time. Of course, fixed-point attractors are just the simplest type of attractor. We'll have many more interesting probably and objects, like for instance limit cycles, which are these closed isolated orbits in state space. So Nancy talked a lot about limit cycles or nonlinear oscillations this morning. Then of course, you have chaos, chaotic attractors, where you have at least one diverging dimensions, eigendimensions in these spaces, and then the trajectories get re-injected into some volume of the state space. And because you have at least one diverging dimension, you have high sensitivity to initial conditions. And so if you start from slightly different initial conditions, trajectories will diverge pretty quickly. So that's all long known, but it actually has quite some implications for forecasting time series. Yeah. So that's why I'm emphasizing this here. There is evidence for all of these different phenomena, or let's say indications of all of these different phenomena in the nervous system. Here, for instance, evidence for limit cycles in motor cortex by Churchland's group. Then you can build more complicated objects or phenomena out of putting together different of these sort of basic geometrical objects, like for instance in this case these changes of selenoids termed heteroclinic channels by Rabinovich and others, which also act as a sort of attractor, so the activity converges into these. But the nice thing about this concept is that you sort of can throw in or delete any of these selenoids, and therefore it gives you a lot of flexibility, for instance, in implementing action or thought sequences. And again, there's some experimental indications that indicate that some of this is indeed, you find some of this in the nervous system. This is here from old work from our group, together with Chris Lappish in Indianapolis right now, and Jeremy Siemens in Vancouver, where we reconstructed from rodents which were recorded with multiple single unit recordings on a kind of working memory task. Details of the task are not so important here. Important thing is that as the trajectories move in or move out of different task stages, they slow down toward the center. Yeah? So there are some phenomena that you find in the nervous system that are also reminiscent of these heteroclinic channels. Okay, so bottom line here is I think there's a long tradition in theoretical and computational neuroscience to think about cognitive processes as being implemented in terms of system dynamics. That is, in terms of attractors, transitions among these, and that's really what is implementing cognition. However, we cannot directly observe that. Yeah? We'll have signatures, we have indications of that, but it would be nice if we could directly retrieve the dynamical system underlying our observations from just doing multiple single unit recordings or from just having time series observations. Okay, so let me point out that these things probably have a strong role in psychiatry. So I'm not going into a lot of details. Those of you who are interested, we just put a review out on that out. So I just want to emphasize like Nancy already did this morning, that we also think that many psychiatric phenomena can basically be explained in terms of altered system dynamics. So I'm going just through some examples. So for instance, if you have overly strong attractor states, with very overly large basins of attraction, then that might explain stuff like tinnitus if it is in early auditory areas, where you have an auditory representation sticking despite the sensory information going away. If the same phenomenon, like overly strong attractors, occurs in prefrontal areas, you might get rumination, or you might get compulsivity, or at a more motor level, you might get motor stereotypies, which are quite common in many psychiatric conditions. And of course, as basically Nancy filled a lot of her talk with that, you get changes in cortical oscillations, which are very prominent in different psychiatric diseases like schizophrenia. If you have too weak attractor states, on the other hand, if your system is sort of imbalanced towards the other end of the spectrum, you might get stuff like incoherent thought that has been described in various diseases, but also schizophrenia, for instance. You might get hallucinations as basically your representations basically just pop out or keep popping out, and you might get attention deficits as you cannot hold on to a memory anymore. What I haven't mentioned so far are bifurcations that probably also play a huge role in psychiatry, where you have these sudden onsets and offsets of diseases, or of symptom clusters. Okay, so I want to echo Nancy here in saying that we think that this dynamic systems perspective is really central in psychiatry, and it's also a central layer of convergence, because a number of different changes that happen at a biophysical level ultimately might give rise to similar changes in system dynamics. And at the same time, as I just tried to point out with this example of tinnitus versus rumination, depending on the brain area where you get these changes in attractor dynamics, you might get very different types of phenomena or symptoms. I think what's important here is that the implications for treatment are potentially that at some level you want to treat the dynamics. So you want to change the dynamics and sort of bring it back into a healthy regime. Okay, now let me start with the actually what I wanted to talk about mostly today, and that is our deep learning or statistical deep learning approaches. So we use recurrent neural networks. So more than 90% of deep learning, I think, is done with feed-forward architectures. We use recurrent neural networks. That means you have a bunch of units which do not just have feed-forward connections, but they also have a lot of feedback connections. Simply put, you might describe such a system by a recursive rule like this. So your state ZT might evolve according to this linear or affine term. Here, within this nonlinearity, you have a connectivity matrix between all your units, and usually these recurrent neural networks are Markovian. That is, you define the dynamics only, or the nonlinearity is only defined on the most recent state of the system. Then you might have a bias term, and you might have external inputs to the system. And these are basically, recurrent neural networks are basically the default these days in machine learning for processing time series information. And they are discrete time dynamical systems in themselves, which are given by this recursive rule in time. So for instance, whenever you talk to Alexa or Siri, that's a recurrent neural network behind it. Yeah. So they process time series. If you put your question, then that is time series of sound pressure levels, and then as an answer you get another time series of sound pressure levels. The same if you type something and it automatically completes your text, or then again it's a recurrent neural network behind it. Yeah, so it's basically the standard by now. Recurrent neural networks are the standard by now in processing moving images, videos, or in processing language or text understanding and so on. Okay, what's important for us is that these recurrent neural networks are dynamical universal. Yeah, so in the sense that they can approximate arbitrarily closely the flow field of any other dynamical system. And that proof rests on two pieces. So one is this famous universal approximation theorem put forward by Sabenko and Funahashi in the late 80s, that you can approximate any function f of x by this sort of series expansion where sigma is a nonlinear, like sigmoid nonlinearity. And then basically the idea is you can use that to approximate the flow field, and then you reshape that as a recurrent neural network. Yeah, so that's the sort of the two key ingredients to that proof. Okay, so that's important for us. Now I want to discuss with you one of the main issues that you have in training these recurrent neural networks on data. Yeah? So these issues are actually quite important if you want to use these systems for reconstructing dynamical systems in the end, and that's the reason why I decided to spend some time on it. So one of the biggest problems is what has been coined the vanishing and exploding gradient problem. And it's the following. So assume you have a series of inputs, ST, and you have a series of desired outputs. Let's call them Z snake T. And you have a generic recurrent neural network description like this recursive rule that I just introduced. And then usually in training recurrent neural networks, you would formulate a loss function. Most commonly, what people do is, for instance, taking the just the squared error loss. Yeah, so these are the squared deviations or Euclidean distances of the desired outputs and the actually given outputs. You sum that up across time and across samples or across different patterns R. And the most common technique that people are using is just gradient descent. Yeah? So basically they try to move the parameters, like for instance these W's, the weight matrix here, they try to move them around against the gradients so that they hit minima in that error landscapes. And then they sort of jiggle this landscape a bit, which is called stochastic gradient descent, to increase the likelihood that you'll end up in a global instead of a local minimum. Okay, so the vanishing exploding gradient problem now refers to the fact if you unwrap a recurrent neural network across some length of time, capital T here, that defines the length of the time series that you want to map, then you have to propagate back your error gradients across these successive layers. And in doing so, these error gradients tend to either explode or they tend to go away. And actually that problem is in itself, you can understand that as well from a dynamical systems perspective. So basically, if you do the derivatives of this error function with respect to all the weights, and you recursively apply the chain rule. Yeah, so you unwrap that for any point in time. You can unwrap the error gradient like this, and then you have in here, just by virtue of the chain rule, you have these partial derivatives of the states with respect to all the other states at some previous time point k. And then the key here is that if you further unwrap that in time, and again, just recursively apply the chain rule, you have these large product terms here, which these partial derivatives are basically just the inner derivatives. In this case, if you refer to the system, your matrix W times the outer derivatives. And then if you have maximum eigenvalues here of this product matrix, which are larger than 1, then your system will just explode. And if they are smaller than 1, then they will just go away. Yeah, so you're exponentially fast. Yeah, so this is a very severe problem unless you tune all the stuff very precisely so that it keeps your error gradient. Yeah, so it is indeed still an ongoing discussion how to best prevent that. So the classical solution, or let me first give an example where one of the machine learning benchmarks that has been invented to probe systems on this vanishing exploding error problem is the addition problem that has been introduced by Hochreiter and Schmidhuber in 97, I think. So the idea is you train the network on adding two numbers, and you provide it with two inputs or two input series, time series. One is just a series of random numbers between 0 and 1, and the second series is a series of indicator bits, which basically indicate to the network which numbers it has to add up, and that's what it has. It has to spit out the sum of these numbers after some time lag, capital T. Yeah? And as you increase capital T, the problem becomes harder and harder, and you push your system more and more to, you know, get out of this vanishing or exploding gradient problem. So the I think sort of still of the gold standard in the field is this long short-term memory architecture that has been introduced in '97. So the basic idea here is to sort of battle this exploding vanishing gradient problem by introducing these memory cells. Yeah? So they are mostly just linear cells which perform an identity mapping. Yeah? So whatever you put in there will stay there forever. And then you introduce different gates. Yeah? And these prevent this information from going, from being perturbed at the wrong times. So you have these input gates which control perturbations into this memory cell, or when information is allowed to enter this memory cell. You have these output gates, and you most commonly also have a forget gate. So these systems, as I said, are still I think quite of the gold standard. Yeah, so in at least a couple of years ago, it has still been one of Google's major workhorses, I would say. But these have a lot of problems. So they are actually very tedious to train. Yeah, and that's something that bothered people for a long time. And second thing is they are mathematically not so convenient. Yeah, they have a lot of product and different terms and in here, and they are sort of precisely engineered to do the job. So they have very different state equations, and that makes them, mathematically speaking, just not so nice. Okay, so here is a system that we are working with and which has a number of key advantages that I want to point out. So it's also a recurrent neural network. In this case, we have the nonlinearity outside, and we have different terms in here. So we have an autoregressive term. A is actually a diagonal matrix, so this is just an autoregressive term. This is our connectivity matrix. Phi is a nonlinearity. In our case, it's just piecewise-linear function, max operator, and that's also called a rectified linear unit in machine learning. And then you again have these inputs, and you have a bias term. So before I go on, I should actually mention that these are also dynamically universal, these systems. You can prove that about these systems as well. Now, one thing that I want you to notice here is that well, okay, I think I'll come to that later. So first of all, let me say why we are using this system. So first of all, it has sort of a modus physiological motivation. Yeah, so firing rates of pyramidal cells and sometimes some types of interneurons, like fast-spiking interneurons, are often quite linear in the physiological range. More importantly, you can access many properties of the system analytically. Yeah, you can compute fixed points. you can compute limit cycles, at least theoretically, and you can compute eigenvalue spectra stability. You can actually transform these systems relatively easily into continuous time, piecewise, ordinary differential equation systems, which comes with a lot of additional benefits for analysis. And most importantly, maybe, you can do very efficient inference with these systems, which is highly important if you really want to reconstruct underlying dynamical system. And I will come to that later. Okay, so now, how do you assure in these systems that they can sort of deal with this vanishing exploding gradient problem? So our idea here is what we call line-attractor regularization. So what we do here is, well, maybe first let me remind you that this A is a diagonal matrix. Yeah? So, and assume now, for instance, just for a second, that all these diagonal weights would be equal to 1. And then if you had not, if you didn't have this other stuff here, then of course it would perform just an identity mapping. Yeah? So whatever you put in there, the system would keep. Now, the idea is fairly simple. We'll just, to our loss function, we add a penalty or regularization term that enforces a line-attractor configuration along certain but not all dimensions of the system. So basically, I think I'll put on this figure here right away. So basically what we do is we push the diagonal for a certain set of units, let's call that the fraction of regularized units, towards 1. We push all the connectivity weights to all other units towards 0, and we push the bias term towards 0 as well. Yeah? So we'll sort of add a penalty term which pushes the system, or which enforces the system to form these line-attractor dimensions along which it can store whatever it wants and needs. Okay, now let's go back. So classical thing, you do in machine learning, you compare your system to the performance of multiple other systems, and then you'll try to show that yours can, of course, outperform everything else in the field. That's not so important actually to us because we are more interested in having something that, that can reasonably deal with these vanishing gradient problem, yet is analytically tractable to some degree. Yeah? So that is our key motivation. But nevertheless, so this is a picture on the addition problem, and multiplication problem is a variant of this, where you, it's a bit more tricky. You have to spit out in the end the product of these two numbers. So basically this just shows the percentage correct as a function of the temporal length, yeah, or temporal lag. So our series is regularized. We call that the Piecewise-Linear Recurrent Neural Network. And actually, it outperforms LSTMs by quite some margin. Yeah? So it does actually better on at least these benchmarks than LSTMs. It does so. Well, okay, so let me just show how the system does solve this task, the addition problem, just to give an example. So in fact, it can do so with just 2 units. And what it does in that case is basically one unit just responds to the input and feeds its activation to the second unit only when there is an indicator bit in addition. And what the second unit does, it really forms a line attractor and integrates the stuff. Yeah? So in this case, you can see that in the state space. So we'll transform that into continuous time. We'll do a state space. And then, so basically, inputs come, the system integrates them, stores them on the line attractor, integrates them, stores them on the line attractor. Yeah? And that's the final result. Yeah, so it does really solve these problems by exploiting the line attractor properties. It also does well on other machine learning benchmarks. So that's another one that is commonly used in this context, so-called sequential MNIST. So you have these handwritten digits, and the network has to learn to recognize them. To make that a time series problem, they are read in pixel or voxel or pixel by pixel, and then after seeing all the pixels, the network has to sort of give the correct answer. And again, this just shows a comparison of our regularized piecewise linear recurrent neural networks to a number of other networks in the field. So it does actually quite a good job. Bottom line that I wanted to make here is, so we now have a recurrent neural network, which is quite simple. We keep the mathematical simplicity of these piecewise-linear recurrent neural networks, yet it's quite powerful. Yeah, so it can produce performance which is at least on par with the gold standard in the field. Okay, now we go one step further. Yeah, so far these systems were just deterministic, as they most commonly are in machine learning. Now we assume that we might have experimental data or empirical observation, let's say. So the idea is now we extend the system. So we'll assume what we have observed, for instance, spike trains or neuroimaging data or whatever. Yeah, we have observed these time series. Let's call them Y, and we have either we are the experimenters ourselves, and we have introduced certain stimuli into the system, or we somehow have just knowledge of external factors that go into the system. And so our problem setting is from knowledge of these external factors and from these time series observations, we want to infer the underlying dynamic systems that we cannot directly see. Yeah, so that's a latent process. And so in the brain, it's certainly a stochastic process in itself. So we now start to model the solar system as a generative recurrent neural network. That is, we'll model it through a probability distribution across both the latent states and the observations Y. And at the end of the day, what we want to get at is nice pictures like this. So we want to, once we train the system on empirical data, we want to retrieve the full flow field and its attractor objects, and we want to have that ready for analysis, basically. So that's the basic idea or setting. And as you can see here, this factorizes in these two parts. So the one part is our generic dynamic systems model, our latent model, the piecewise-linear recurrent neural network in our case. And then we can couple that to different observation models. And by observation model, I mean the conditional probability of my observations Y given my latent state Z. Okay, so in general, our framework looks like this. So we have this latent dynamic system, and as I mentioned before, it's a recurrent neural network. So we assume that our states ZT are conditional Gaussians, conditioned on the previous latent state ZT minus 1, and the conditional mean is given by our piecewise-linear recurrent neural network formulation that I introduced previously. And then depending on the type of observations we have, we can couple that to different observations models that might describe different modalities. And we also, as I just mentioned, take different external stimuli or inputs into account. So just to give you an idea of what these models might look like, these observation models. So for instance, if you have multiple single unit activity, it might just depend on the current state ZT. And you might want to model that, for instance, by a Poisson model, where the parameters of your Poisson process are, again, some function of your underlying latent state. And this function G might be something very complicated in the end in itself. Yeah, it could be, for instance, multi-layer perceptron. Then for the calcium dynamics, yeah, so assume we have a calcium imaging data here, but the same holds, for instance, for fMRI data. You might want to assume, because you have this filtering in place, that your observation at any time t depends not only on your last state, but on a series of last states, on a sequence of last state. Again, you might want to model that through conditional Gaussians, where your parameters of that Gaussian can be, again, in principle, be any complicated function of your set of states, latent states. And for behavior, for instance, you might want to assume a categorical model. So depending on the situation we are dealing with, we couple our latent model to different observation models simultaneously, and then we'll try to use all this data simultaneously to infer our latent process model. And once we have that, and the inference in our case is either goes by maximum likelihood or by Bayesian inference, and then in the end, once we have that model, we can analyze that. That's the hope. Yeah, that's the basic idea. Okay, so now here's one thing that I really want to emphasize. So what we are after is reconstructing really the underlying dynamical system. We don't just want to do time series prediction. Yeah, so we actually want more. We want to recreate the governing equations in our recurrent neural network. So let's take as an example the Lorentz system described by 3 differential equations. So it gives rise to these famous butterwing fly attractor structure, and this is one of the time graphs, one of the variables of the Lorentz system. So the idea is experimentally or empirically, we'll just have access to noisy samples from the true trajectories. Yeah? And this is what we want to use to infer our recurrent neural network. And then, and that's an important step, once we have inferred the parameters of our recurrent neural networks, we want to be able to sort of, well, basically, at that point, we'll ignore the data, we throw them away, and then if we generate new data from our recurrent neural network, we'll simulate it, then these data should actually look like the geometry of the Lorentz attractor. And that's actually one actual reconstruction done by training a recurrent neural network. Okay. So how much time do I have left? 20 minutes, yeah, okay. So maybe I don't go into much detail about this, but basically there are 2 main inference frameworks we use. The one is more appropriate for small data, which is expectation maximization. Actually, Emery has worked quite a bit on this, and some of our work actually built on some of his papers. The basic problem you are facing, just very briefly, is that you have these high-dimensional integrals where you have to integrate. So to get the likelihood, you have to integrate out all these latent state paths, and that's a tricky problem. And I think I don't go into much detail about that, but basically what you do is you introduce a lower bound, and you can derive this lower bound, for instance, by Jensen's inequality. You sort of introduce a proposal or variational density, then you can pull the log term inside here, and then you can rephrase this in different ways. I think I'll skip all this. Bottom line is you use this evidence lower bound in expectation maximization. That's what you maximize, and your expectation maximization basically consists of 2 steps. So the first step is you try to you basically dissect the problem in finding your probability distribution across your latent states, and then you assume that to be known, and then you go for the parameters in the second step. Yeah? So first you try to obtain this probability distribution across latent states, assuming some fixed theta of parameters, and then in the maximization step, you assume that you have your probability distribution known, and you go for you maximize with respect to your parameters, and then you iterate these 2 steps until convergence, if it converges. So I think the bottom line here is, and I can tell you more about the details afterwards, but basically for piecewise-linear recurrent neural networks, you can design very efficient inference algorithms. Yeah? So you can really exploit this piecewise-linear structure of your model, and we do that by a certain type of fixed-point iteration algorithm. And then you can analytically derive most of the moments of your posterior probability distribution. Yeah? So that's analytically tractable, yeah? And that makes it efficient and fast. Yeah? So that's good. However, if you go to large data, you do need something else. And again, I want to be brief here, and I guess many of you might know this framework, so we'll use basically sequential variation autoencoders for that. Sequential variation autoencoders is at this time a very popular framework for inference in machine learning. It also tries to maximize the evidence lower bound, just like the expectation maximization algorithm that I introduced previously. But it, and in this context, we call Q often a variational density. The key point here is because these integrals are you often don't have them in closed form, they are not tractable. You approximate that by sampling estimate. So you try to sample from your posterior your latent states and plug that in here. But then the common problem here is that once you sample from that posterior, you basically knock out your parameters in that function, because ZL doesn't contain explicitly these parameters anymore, so you cannot do a gradient descent on these parameters. And so what you do is you replace that, that's called the reparameterization trick. You replace that this density here by a deterministic function of an unparameterized density. That could be, for instance, just the standard Gaussian distribution. Basically, this trick you can do for all exponential family distributions. You cannot do that for all distributions, but you can do that for all exponential family distributions. Okay, and then you can do actually standard gradient descent on this. So, and that's the second framework we are using because it scales very well to big data. Okay, now I come back to one important point that I think I already implicitly at least made previously, and that is, I think, for reconstructing dynamical systems, it's important to note that simple prediction errors in time may be not sufficient or even meaningful. And that's simply if you have a chaotic system, as you usually always have, if you are dealing with the brain or with behavior, then even if you have just minuscule differences in the initial conditions, it will quickly diverge, and your, let's say, mean squared error on these two traces is completely meaningless, although these two systems are exactly the same. So these two traces here come from exactly the same system. So your match is perfect if you found this system. And so that's basically why we are trying to quantify agreement in state space and not in time. So we'll do that through a certain type of Kullback-Leibler measure. And this graph here basically just illustrates that although your match in time might be lousy, the attractor geometry might be perfectly captured, and vice versa. You might have fitted a simple limit cycle, which does a pretty bad job on reconstructing the Lorentz attractor geometry, yet it might express the same fundamental frequency, and for that reason actually show quite low mean squared error. So these two things can diverge. They can be different. Okay, so here's our setup again. So we'll assume we have some nonlinear dynamic system. In this case, here just for illustration, the Van-der-Pol oscillator. We have noisy samples. We infer from that our network and our parameters. Then we'll basically sort of throw away the data. We generate new samples from our inferred network. And then we quantify the agreement with the true system by this Kullback-Leibler divergence across space and not across time. So P true is a true probability distribution in state space, and this P gen is the probability distribution that I get if I simulate my network and generate new observations from that network. Okay, so this is just another example of Van-der-Pol oscillator. This illustration just shows that this maps quite well on examples, or captures quite well this Kullback-Leibler measure the attractor geometry. If it's small, then you see that these reconstructions actually fairly well capture the geometry of the true underlying attractor, and that also correlates with other measures, like for instance Lyapunov exponents. Okay, so this is actually a little video that's run in our group did. So it's a 10-unit recurrent neural network, piecewise-linear recurrent neural network, and it's a 3-dimensional subspace. So I think it's a unit somewhere down here that are illustrated here. And it shows that also very low-dimensional networks are already sufficient, for instance, for reconstructing the Lorentz system. Okay, so one more important point. This line-attractor regularization that I introduced previously is actually very important for capturing systems with very many different timescales. Yeah? So that's illustrated here for a bursting neuron model. So this is the true trace generated by a bursting neuron model, and this here is one after training freely generated from the fitted piecewise linear recurrent neural network. Yeah, so this is not a fit to the data. It's once we have trained the model on the data, we generate new data, and they capture the underlying attractor geometry. And so in a nutshell, basically, you have created here a bursting neuron model as a piecewise linear recurrent neural network. Yeah, you can use it now as your bursting neural model implementation. And the regularization turns out to be quite important for that. Yeah? So what this graph shows is that as you increase the regularization, it doesn't affect so much the high frequency components, but it does affect the low frequency components quite a bit. Okay, now I have like 10 minutes left. Yeah. So I want to finally come to my application examples in psychiatry. Here I'm using two different example setups. So one is for fMRI data, where we couple our process model with an fMRI observation model, which accounts for this hemodynamic response filtering. So what I'm showing here are some results on a radial arm maze, human radial arm maze version of the animal or the rodent task. Again, the task details here are not really so important, but basically the subjects here have to venture in all these arms, collect gold coins. They do that in a virtual reality environment. Then there's an enforced delay, and after that delay, they have to sort of go into the arms they haven't been in previously and have to, collect all the remaining gold coins. So first thing I show here is just for two different subjects that in these reconstructed latent trajectories, and these are just subspaces of a 10-dimensional space, these trajectories actually segregate quite well according to task period. Yeah? So, and to my experience or our experience, these are really models recreated on an individual basis or inferred from individual subjects on a relatively short time series. Yeah? So that you get the segregation, in my mind, is not trivial. Okay, so before I actually move on, you might ask, how can you actually be sure that you captured the underlying dynamic system in these empirical cases? Yeah, so for the benchmark systems, of course, we know we can compute our Kullback-Leibler measure directly on the state space that we have, and then we'll, we know how good we are. So is there any assurance that in an empirical situation you captured the underlying dynamic system? So our idea is we use two distributions to which we have access to. Yeah? So the first one is we have a posterior estimates of the latent states given the observations. Yeah? And for instance, it might look like this. Yeah? So this is just one fMRI example. And now we compare it to a second distribution, and that is the basically the prior distribution across latent trajectories. And the idea behind that is, it might, in a good example, it might look like this. Yeah. So the idea behind that is, if if you truly have captured the underlying attractor geometries, then your inferred posterior should be a good representative of your prior distribution. If your prior distribution goes somewhere completely else, which often happens, yeah, so it can go into fixed points or something, then you are far off. Yeah? But if this is a good representative of your prior distribution, that's the idea, maybe you have reached a good match. Okay, so we quantify that through another Kullback-Leibler divergence between our inferred posterior over latent states given our observations and between the generated distribution or prior distribution in the state space. So this is usually a high-dimensional integral, but it turns out that you can approximate both these densities, the inferred posterior and the generative distributions by Gaussian mixture models. And for Gaussian mixture models, we have actually quite a good analytical approximation to the Kullback-Leibler divergence. So that was pointed out in a paper by Hershey and Olson. So you don't actually have to, you don't have to go through all these high-dimensional state spaces. You can fairly easily compute this analytical approximation. And that actually correlates quite well with the Kullback-Leibler divergence that we get for the situations where we do have the benchmarks. Yeah. Okay, so these are just some observed and predicted bold traces. We also often observe that the power spectrum of the data and those of the generative network, at least that our generative network captures quite well prominent frequency components in our real power spectrum. And I'll illustrate that with another simple video. So we call it the fMRI Turing test. Are there any fMRI experts among you? Yeah, I'll read you certainly are. Your job is to find out what is fake and what is fake data created by the recurrent neural network and what is real data, left or right, blue or yellow. Yeah, so actually I can't even tell you myself because I don't know. I always forget about it. Yeah. Yeah, I don't even know whether that's correct. I'm sorry for that. Okay. Yeah. So maybe after some time you still will find differences, right? But anyway, yeah. So these recurrent neural networks are actually quite good in extracting the dynamics from even this short fMRI time series. Okay, and if you now look at the state spaces, they do actually have a number of interesting objects in it. So for instance, this is from one subject through three simultaneously existing limit cycles. Some of them are fairly complicated, or this is multi-stability between limit cycles and chaotic attractors. We didn't do a whole lot of analysis on that until now, but what we saw is that somehow correlates with performance of the subjects. So for instance, we don't quite know how to interpret that, but it seems to be the case that if you get more unstable objects and less stable ones, the performance is better. Yeah? So our, I don't know whether I should actually pop that up here, but maybe I do. So maybe it has to do something with state space complexity. Yeah? So certainly the state space complexity increases with the number of unstable objects you have in there. And so maybe that correlates somehow for some reason. We don't know yet with better performance. So the bottom line here is just you do find correlations with different behavioral measures. Okay, now I have like 2 minutes left. So let me give you at least one example. For instance, we have that same task for schizophrenics and for control group. These were studies performed by Florian Berner in Andreas Lindenberg's group. I already told you, you can analyze these recurrent neural networks now. You can, for instance, look for all the fixed points. You can compute the eigenvalue spectrum. And what we observed, for instance, in this case, is that for schizophrenics, the eigenvalue spectrum seems to be it has more unstable modes. Yeah? So so if you are around 1, you are neutrally stable. Yeah? So it has more unstable modes, and that seems to be connected to having more inhibitory weights in the recurrent neural networks inferred from schizophrenics. And so that you might have more unstable fluctuations in these networks, maybe. Yeah? And these weights actually also correlate with other scores, like the PANSS General Psychopathology score. Yeah? So there are some, so we'll just started this sort of analysis, but there seem to be interesting bits in there that might be able to tell us something. Okay, so I'll briefly, I think I don't go into details here, but basically another line we are following is inferring these networks also from mobile data. And what's quite popular with, in psychiatry these days are these ecological momentary assessments, where subjects are asked to fill in many emotional, motivational scores each day on some rating scales, and then you might have other modalities in addition. And then the idea is you can use your trained networks in the end to do something like risk forecast. And you might also use them to, for instance, predict the effects of medical interventions. Yeah? So you can simulate, if you have information in your training set about medical interventions, then you can, for instance, look what happens if I leave them away, and then you can analyze what happens with different types of drugs, like lithium in this case, or this one here, and you see that you get effects with some drugs and not with others. Yeah? Sorry, I'll just I think I'm running out of time, so I don't go into more details here. So the take homes here are basically we do think that dynamical system theory is quite important and can give a lot of new insights or new perspectives in psychiatry and potentially the treatment of certain diseases. I introduced to you a framework based on deep generative recurrent neural networks for inferring dynamical systems from data that we can use for reconstructing dynamical systems from fMRI observations or mobile data or whatever you have from time series data. In a sense, it enables diagnosis of patients in systems dynamical terms. Yeah. So because you basically, once you have inferred them, and because they are mathematically tractable to some degree, you can start to dissect them, and it allows to predict individual disease trajectories. Yeah. So that's a point that I should emphasize as well. Ultimately, we retrain them on individual subjects. Yeah. So it's personalized in this sense. Yeah, so that's what I just said. Yeah, so you can do that in a personalized fashion. So last but not least, this is a list of collaborators. Yeah, so mobile data will often do with Uli Reininghaus these days, and Ulrich Ebner-Prima, who is not on this list, I'm afraid. Heike Torst, Florian Behner, Andreas Maurer-Lindenberg did the neuroimaging work. Then from a lot of people from our group contributed to that, but I want to emphasize or highlight Georgia Copper, who does all the computational psychiatry stuff, and Dominic Schmidt, who worked on the line-attractor regularization. So that's it. Thank you for your attention.